where AI is R in N1. So I would say that AI complement would increase to a complement. Okay? Where these AI complement are in M actually. Okay? Why this is the case? Because think about it. If AIs are in N1, by definition, AI complement must be in M. So these all of AI complements are in M. So I have a sequence of, I have an increasing sequence in M that is increasing to a complement. So this implies that a complement is what? Is in M. And if the A complement is in M, then A must be in calligraphic N1. Okay? So therefore N1 is a monotone class. Okay? Why this would be true that it contains A naught? Just think about it. What is an A naught? So A naught, in A naught you have the unions, the finite unions of what do you call? Okay, let's show it explicitly. Okay. So what does follow from here? What does follow from here? And for the rest of the properties, I'm gonna similarly create an N2 and N3. So I'm leaving that for you as an exercise to do the rest of properties. Okay, so what we have shown so far is that M1 is a monotone class. Okay, so we showed it that it's a monotone class. So the next I would like to show that N1 contains A naught. First of all, give a thought. Does this follow trivially? I need to. Okay. Let's do it then. So here's the thing. It should be same. So let's take A as what? Union of I equal to 1 to infinity. No, not infinity. But N AI from A naught. Okay, so that's an abstract element in A naught. Okay. So my claim is that this A must also be in A naught, in N1 actually. And how can I show it? Think about it. So the key question, in order to show that A must be in N1, I need to just show that I can write these guys, this union, as an increasing, okay, so like a, what do you call, as sequence. So I need to construct an increasing sequence, okay, or a decreasing sequence, okay, that decreases to A or increases to A. And how can I construct an increasing sequence or a decreasing sequence? It's simple. So if I say that if I'm defining B1, that is A1, and if I define B2 to be A2 minus A1.
Union
do increasing or decreasing?
Okay. If I'm saying doing increasing,
So union.
Union.
I need to show A1 union A2, okay, and so on and so forth. Bn as union of I equal to 1 to n AI, and I'm saying Bn plus 1 are, maybe Bk is empty for all k bigger than or equal to n actually. Okay? Maybe
equal to n.
k bigger than n. Okay? if this would be the case, then I can say that A is what? Or maybe I will say that BI, okay, is an increasing sequence, okay, such that are increasing to what? A. How can I make sure that this sequence is indeed in N1? So you have to also think about that why these guys are in N1. Then the argument would develop.
A naught belongs to sir. A naught in M, sir.
Okay, so
So sir,
M is
each
subset.
AI is in A naught, and each AI is in M.
M is in
And
N1.
since each I complement because of algebra is also in A naught, so that would each
you
AI
need to
right.
note that. Okay, so what should I write? Since each
AI
AI is in
A naught,
A naught,
so which is in A M.
okay, which is contained in M,
Hence AI,
okay, hence
AI
AI,
is in M.
AI
AI is
belongs
in
to
M.
M.
And since
M.
AI from A naught, so AI complement should also be in A naught and in M. So therefore,
A complement.
A and
so
sir.
this means that by definition, AIs are the kind of sets whose complements are in M.
Yeah, exactly.
There must be in calligraphic N. Okay. So what does this show that? Okay, and hence I can say that BI is also
Belongs to
and one that. Okay, for all. Can I say BI?
Sir,
Yes, sir.
it's a jump for me.
Again, jump it.
For me, sir.
Okay. So AIs are in N1.
सर हम अगर BI कॉम्प्लीमेंट को कहते कि M तो फिर
BI complement to. So instead of saying
जब
so instead of saying AI, I say that okay, since BIs are from A naught. Okay, so let's replace.
Yes.
So I don't need to rewrite the argument. Okay.
Right.
So hence BIs are in M. Since BI complement are also in A naught, so therefore
Yeah.
BI also in N. Thus, what we concluded is that I have found
The sequence
an increasing sequence, okay, in N1 such that
BI increases to
BI increases to A. And since N1 is a monotone class, so this A, which is in calligraphic A naught, must also be in, okay? And what does this shows? Hence, I would say that N1 is a monotone class,
Continuing.
Continue.
okay, containing, okay, A naught. So N1 must contains. So let's say N1 must contain M, and M contains N1 by definition. Okay. So N1 is same as M. What is the benefit of getting this is that the property that we wanted, okay, in order to show M to be a, what do you call,
Sigma.
a sigma field, we wanted every element of M to satisfy this complementation property. But since the M is equal to N1, and for N1 you have this complementation property true, so that for the M is going to be also complementation property true. Okay? So what you have to do next is that prove 2 and 3 by the same strategy. So in other words, consider an M2 for which you have this countable union
Sir,
property.
how do we prove M is contained in N1?
What do you mean by
M is contained in N1.
that?
M is contained in N1. We wrote. the last line.
This one.
M is contained in N1. Yes, sir.
This one.
N1 is contained in M is what we proved in the first part.
Okay, so we
The
prove
second
it.
thing, M is contained in N1.
Maybe this is okay. This is true by definition.
N1 is a part of M. It's clear. Sir.
Okay.
But how N1?
So that's what we have proved just by doing all that. So he said M is okay. So here's an argument. Maybe you missed it. So M is the smallest monotone class that contains A naught. Okay, that's what our assumption is. Okay. That M
Is the smallest.
is the smallest monotone class containing A naught. And now I have found another monotone class that contains A naught.
Okay.
So the N1 should contain it. Okay.
Thank you, sir.
So we will try to prove second and third property based on second property, maybe other properties. So the exercise is to complete the proof. Complete proof, okay? Not that difficult, but yes, it's giving a good sense, and that's a very good trick actually. And we used it previously while we were doing proving or constructing product sigma-algebra and product measure. But here it's a bit different because we are dealing with a different structure. So maybe we need to do more effort actually.
Strategies.
Okay, the strategy is same. Strategy is same. All right. So once we have this, then so we have 15 minutes around. So let me state, give you an intuition for Fubini's theorem. I'll not state it precisely now, but I'll give you a bigger picture that what does it say, then we'll try to prove some auxiliary results before proving that result. We're going to do it maybe in tomorrow's class, but let's have a beginning. So what I want from this result is basically that you must keep this thing in header. Okay? So what does this theorem is giving you a liberty that if you have an algebra and you want to prove something sigma algebra, okay? If the underlying collection is an algebra, then it is sufficient to prove it a monotone class actually. So if you show it that it's monotone class, it's sufficient to prove that that the given connection is a sigma algebra actually. Okay? It kind of gives you the connection. Otherwise you need to maybe prove much weaker condition than. All right. So here's the rough sketch that we would like to do today and in the first part of tomorrow's lecture. It's called Fubini's theorem, and it's really a generalization actually. It's a kind of a most generalized version of Fubini's theorem. So in other words, if something is okay, if the Fubini theorem is true here for abstract measure, obviously it's true in in your 3D and 2D calculus. What is it actually as well? Because all those are particular cases of what you have here. Alright, so imagine I have two measure spaces, X as sigma algebra A and measure mu, and Y, B and mu. Okay? If we have this, then we know this creature, this mu and the product nu, in other words the product measure of mu and nu. We know, we constructed it in the last discussion, we know that it's a measure, or it's a product measure on the product sigma algebra, okay? Plus infinity, okay, so it's a product measure on the product sigma algebra. And if you remember, the product sigma algebra is the sigma algebra that is generated by the collection of all rectangles. And in fact, we proved that the collection of all rectangles is an algebra itself. So that's a sigma algebra generated by the algebra of rectangles. Okay, so that's what we did last time. So keeping in view this, I would like to take a function f, okay, from x to the two arguments x plus y into the plus infinity, okay, plus infinity, or we can take it as a map from x plus y into r, but f is non-negative. And set, so to be consistent, because we are reading Bass' book, so to be consistent with the notation of Bass, is defining, as we defined previously, the section of a rectangle. Now I want to define a section of a function actually. So if I have a function, so pick x from the space x, okay, and define, okay, so f. So in other words, what I'm saying is that, so f is a function which takes two arguments, x, y. So if I fix one argument, then I can see the function as a function from y into 0 to plus infinity. Okay. Maybe that is to call this as r, and let's call this f as non-negative actually. Okay. This should be a better thing to call. So if I fix x here, then I can treat that as a function of y actually, from y to. So that thing I'm denoting by, so I have a f, and I'm seeing the section of x, the section of f determined by this x, and I'm defining this as a map, okay, from y, okay, into r. Obviously it's going to be non-negative as well, because f is non-negative, as that the Sx of f when operated onto a y gives me f of x y. Okay? F of x y. While okay, for all y and y. So x is fixed. So I'm calling this as a section of f. Section of f determined by x. Right? Similarly, I can also determine section of f with respect to y. So you can have an intuitively guess actually, think about it, that if I assume this in addition that f is a measurable map, in other words with respect to this sigma algebra, if this is a measurable map with respect to this sigma algebra, then this would also be a measurable map, but with respect to, in this sigma algebra. You're getting the point? And if this would be the case, okay, imagine that, I haven't verified it, but if this is a measurable map in this sigma algebra, then I can also talk about this integral. Basically, I know that if a map is integrable and measurable, then I can also talk about this integral. So in other words, I can compute this Sx of f of y. It's integral with respect to which measure? Nu. Okay? With respect to nu, because you are in this space. Okay, and I'm putting a y here so that I can give a reference that I'm integrating with respect to the y. Are you getting the point? So, if f is measurable, this section is measurable, then I can also show it that this guy, in other words, if I treat this as a map that takes x and gives me such kind of an integral, so this would be a map from where to where. So it's going to be a map from x into the r actually. Okay? And I can show, or I will show basically, that this thing or this map is imaginable. Is what? Is imaginable. So I'll show that this is imaginable.
Sir,
Uh-huh.
y to r cube,
I'm sorry?
x to r cube.
No, no, think about it. So if I'm integrating with respect to y, okay, and this guy contains x actually, so the result that I'm gonna get, like in Riemann integrals, in the terms of the x. So that would be kind of roughly an expression in x actually, or something that depends on x. So I can treat this as a map that takes x as an input and give you, an expression in the terms of x actually. And I can show that it's immeasurable. And if it is immeasurable, I can even integrate this function actually. So if I'll integrate it over x, this, okay, fx, okay, of y, d mu y. Obviously, I need to integrate it with respect to mu and x. Okay. So the Fubini theorem says that if you compute this integral, okay, if you compute this integral, it turns out that this integral is equal to the integral of f. Okay, it's equal to the integral of f with respect to the product measure. With respect to the product measure, and obviously the space, underlying space here is x cross y. Are you getting the point? So basically, in order to reach here, I need to prove three things. Number one, section is measurable. Number two, this map is measurable. And third thing would be to show the equality here. I mean, if you see, interestingly, I can show something similar for the section of y actually. And if I do the precisely same thing, I can also show that this is same as the integral, okay, of section of y. Okay, if you wish, you can put a capital Ty, the way Boss puts it. Okay, f of x with respect to d mu x and d mu of x, and this is equal to basically
Why is that last?
y square. Okay, and this is equal to the same guy, and hence you can have the equality of these guys. And this would be what? This would be kind of the change in order formula, okay, for such kind of integrals. Okay, so once this is true, then this would be obviously true, and you have, this equality that you can also switch. What do you call it? The integrals. Okay. If your integrand is good enough, and this whole story, in its sense, is called the Fubini's theorem. That's the Fubini's theorem.
So what are assumptions on f and measurability?
So the only assumptions for movement are measurability and non-measurability. Okay. But in exercise, one of the exercises to generalize it basically, that when if f is complex valued, in other words, f can be written as, or f is general actually, f plus and f minus, then we can also prove the same kind of a result. But for us, this would be enough. Okay. We can assume the same kind of a result for general f and complex value as well. So that's essentially bigger picture. So I think we're almost done. So we're gonna work on this picture tomorrow.